Proficiency in pointer manipulation, dynamic memory allocation, constant insertion, deletion methods, a linked list is such a fundamental data structure that a lot of other, more advanced algorithms like skip lists rely on its fundamental concept. And I bet you if you plan to be a true eng, that just sits deep within your engineering thinking. You'll learn how to build a linked list from scratch and what each method does, explain in detail, but what sets this video apart is we'll time freeze the debugger to visualize the pointer manipulation in real time. Believe me, this really helps solidify the concept. And we're gonna do all of that on 10 most common LeetCode linked list problems, all broken down in excruciating details. And we'll get to that, but first, there are two important data structures for memory management that you need to understand that build the foundation of the linked list. Stacks. And think of a stack like this, just a pile of boxes, where the first box sits at the bottom of the stack. And each box can be removed or added and viewed at the top. But the boxes further down aren't instantly available. That is, to get to a particular box, say the first box, you need to take off each box that sits on top of it, which gives rise to its second naming. Last in, first out. So let's actually build what you just saw. Create a class called stack, and inside its construct method, let's define an attribute called self items. This is a list where we store all those boxes. It has three methods. We have push, what adds a box, in Python is called append, pop, what removes the last box from the top, or the last index in the array, and peek, just returns the last box from the top, also the last index in the array. Now, I want you to think about drag racing organization. Yeah, like those guys that organize racing events. Imagine how their race management software for time clocking cars on a drag strip might actually work. Hypothetically, of course. I mean, really imagine how it might work from the inside. Well, it probably resembles something like this. Once the Christmas tree or the starting light turns green, the drag race function is called, which itself calls launch function, which then calls calculate quarter, which then calls print time slip, which does the calculation but will simply pass. Notice how we've just built a call stack. For better demonstration purposes, let's actually visualize what's happening here. When the drag race function is called, it's being pushed onto the call stack. It has two functions to call, right? We have launch and update the results time. But of course, it's going to call the launch function first, so it's being pushed onto the call stack. The launch function then calls calculate quarter, so it's also being pushed onto the call stack, which finally calls print time slip. Now in our case, it effectively does nothing, so just passes. So this is at that point, it returns none, or in other words, it just pops off the call stack. And since it returns none to calculate quarter, the calculate quarter returns none as well. So it's also being popped off the call stack. Cool. We've finished our launch function. Now it's time to call update results time. Push it onto the call stack, update results time, and once it's done, return back to the drag race and pop it off the call stack again. And now we're left with the drag race, which then effectively also gets popped off the call stack. Now, if we come back to our drag racing management software example, this is what that call function looked like. As you can see, it takes a function as a parameter, and using our stack class that we've built previously, pushes that function onto the stack. It'll then recursively keep calling each function right up until we hit the base case. And once we do, it'll start popping every function off the call stack. Here's the output. Pause the video if you need to and try to really internalize it. Now, the time complexity of all push, pop, and peek methods in a stack is O of 1, so constant. But if you were to retrieve an item, the relationship will actually be linear. That is big O of n. Because think about it, right? Every item has to be popped first to get to the item that you're looking for. So arbitrarily, if it takes 1 millisecond to register one vehicle for the race, it'll take 7 milliseconds to register 7 vehicles. That's your linear time relationship. Cool. Now let's visualize the queue class. Imagine a memory module. But every item, instead of adding it to the back of the array like you'd normally do, it instead is being added to the 0th index. So effectively pushing all the items that are greater than that index to the right in memory. So the enqueue operation has actually a linear time relationship. And that's the crucial difference in time complexity compared to something like a stack. However, when it comes to operations like pop, peek, and size, their time complexity is still constant. Now the queue class is similar to a stack, but with some updated naming conventions like enqueue and dequeue instead of push and pop, and the major difference in the way we add items. So inside of this enqueue operation, every item is being added to the 0th index. This is your insert in Python. And so that you can better understand queues, pretend that you're building a matchmaking app for the drag racing track, of course. Here's the, idea of the app. Participants can join a matchmaking queue to find other drivers for a drag race. But if their vehicle is less than 500 horsepower or more than 1500 horsepower, they'll be disqualified from the race, just like that Supra. Otherwise, if it's within the range, we're going to push that participant to the queue. Lastly, we'll check if we have enough participants to start the race, and if so, we'll pop the first 2 drivers and start the race. Now we'll use the queue class we built previously to manage our matchmaking process. So this is a function that we need to complete. Essentially what it does, it simulates drivers joining and leaving the queue. As you can see, it takes a instance of a queue class and a participant. Participant is just a tuple that contains number 1, vehicle, and number 2, its horsepower. So let's build the logic right now. First, what I'm going to do is I'm going to create 2 variables called vehicle and horsepower, kind of like slicing that tuple up. Next, I'm going to check if this car has at least 500 horsepower and at most 1500 horsepower. And if so, we're going to enqueue that into our waiting queue. Else, we're going to disqualify that or reject the incoming request. In this case, I'll just say pass. Now, don't forget that we also have to check if there are at least 4 cars on the track. And if so, we're going to pop the first participant, in our case it'll be queue dequeue, and the second participant, queue dequeue. Now, I want you to actually pay attention here because whenever we dequeue or pop an item from the queue, we're popping the first item that got in. That's where its second naming comes from. First in, first out. And to indicate the operation when successful, we're going to return the following string. The first participant is racing second participant, where the first participant is the first participant popped from the queue, and the second participant is the second car popped from the queue. Now, if there were less than 4 cars on the track, or if we weren't able to find more than 4 cars on the track, we're going to return the following string, waiting for a full track. So let's test. Imagine these are all our participants' cars. Not bad. Using our queue data structure, we're going to iterate through each participant in the test case, and we're going to pass that participant into our test function. Again, to make it easier to work with, I sliced that participant tuple into model and horsepower, but remember, all the logic that we've just built will rely on that matchmaking function, so we save its result. And as always, I'm gonna let you analyze the output for yourself, pause the video if necessary. And now, do you remember what the queue looks like? Well, I want you to mentally uncreate that memory array, and instead, imagine that each cell has its own block of memory containing the address. It is similar, but instead of every item sorted next to each in memory, we can access the item by directly indexing into. Knowing that to be true, here's what building a linked list looks like. Say I want to remove the first, also the head item that I've added. Well, the way it is done is as follows. I set the head variable to whatever block of memory, or simply node, its pointer is pointing to, effectively reassigning that head variable from originally the purple cube to what the purple's cube was pointing to, the green cube. And was is an upward word here actually, because that purple cube doesn't exist in memory anymore. I try to indicate that here by fading it out. By the way, if we were using C, we would need to manually free that node, but in case of Python, it's taken care of by the garbage collector. Now, I want you to remember, in a linked list, there are no indices. We literally need to walk each node off the list because the only way to get the location of the second item in a linked list is to look at the pointer of the first item. So, say I wanted to set the head, currently the green cube, to point to the red cube. I'm going to walk each node up to that red cube and then change the head's pointer to point to that red cube. And the current linked list that you're seeing right now has only 3 nodes. So do you still remember those drivers from that waiting queue? We used the queue class to build that. Let's do it again, but this time around, we're actually going to design it as a linked list. First thing we need is a node. And you can think of a node as that cube that you just saw. Now, in our example though, one node will represent a car. So I'll just call it car. It'll have 2 attributes in its init method. Model, which saves the reference of a car's model, and next, the reference to the next car in line. It's not pointing to anything right now, so just call it none. This method, I'll explain later. Now, racetrack in our case is a linked list class, which, as we're building a queue, will have a purpose of keeping track of the first item being added or popped, kind of catering to that FIFO algorithm if you remember. In this init method, it'll only have 1 attribute, which in a linked list lingo, we call a head. Set it none for now. These 2 methods, I'll explain in just a minute. So let's build a queue. These are contestants, and all these cars are sorted in descending order. So SR the Demon, for example, would be the first car here. First, what I'm going to do is I'm going to actually create a racetrack and assign it to a racetrack type. Then I'm going to set its head variable, which is currently none as you remember, to the first car, on the racetrack. I'll just pick super arbitrarily. Next, I'm going to iterate through each participant in that test case, and for each iteration of the loop, I'm going to call my test function, inside of which I'm going to create a node, aka car with our participant, and assign it to a variable called vehicle. And now, I want you to jog your memory back to that enqueue method. Those items that are shifting to the right to make a space for a new item in the array, the enqueue thus has a linear time complexity. But same here. Because we don't know where the end is, we literally have to walk each node until we reach .null. And the way we're going to figure that out is by using this helper function, getLastVehicle. Inside this function, we're going to save the head of our linked list, so the first car on the racetrack, which as you remember is Supra, and we're going to save it into a variable called current. We're then going to throw it inside this while loop, which will advance the current variable. So it'll keep iterating until it finds the car whose next attribute will be null. Only at that point do we know that we just found the last car on the track. So we'll terminate, we're going to return that last vehicle, and we're going to save it into its respective variable, which is last vehicle. And since we know that Super is currently the last car on the track, the Demon will be the next to it, effectively now making Demon the last car on the track. It might feel like queues, but heading to the wrong end, because it is. In the output here, I even added arrows to indicate the flow of operation for clarity. And if you're wondering where I got those arrows from, you're asking the right question. Let's cover a couple Python dunder methods that use heavily throughout this video. First, iter. This is a built-in Python dunder method that returns the iterator for the given object. Like, if I wanted to represent a line of 4 cars here, cars would be a class with 2 attributes, self-length and self-current. Let's just set it to 0 for now. Iter is what allows the car class to be iterable in the first place. And next is what keeps the count. So if I iterate, I have 4 cars, each printed on each line, as you can see. Now, if I didn't have the iter method at all, the line of cars wouldn't be iterable and Python would just raise an arrow. But next method would still keep the count if we're gonna print it enough times. It's a very high-level explanation. Anything lower than that would be too out of scope. Just a helpful method to be familiar with. Now, after we save this help hat into a temporary variable, we put it inside this while loop. Because remember, the only way to get the location of the second item is to look at its pointer. Yield is an interesting one, and honestly, I didn't know how to explain it better than just code it up. Watch. So yeah, it's like a return that returns the result of a function, but then continues from where it left off. Now what about wrapper? If iter makes something iterable, then wrapper makes something, well, printable. Here we use a loop, thanks to iter, which advances the head of the list to extract some useful information from nodes. Like in this case, we're extracting the car's model. Once it's finished, we'll have a nice list of strings, so I just join them with those arrows representing a flow of added items. That's what those dunder methods do in a nutshell. Okay, so this small race management software is fine, but let's say the clock operator made a complaint that your software lacks the feature of adding cars to the head of the queue. And it's also slow as fuck. You need to optimize it. Here's some things to remember though. In Python, you can insert elements into list using the standard methods like insert and append. And for remove elements from a list, you can use remove or pop. Insert and remove operate elements at a specific position in a list, while append and pop insert or remove elements at the end of the list. So basically, to append or pop an item at the end of the list requires just one step. It's constant time. And as you already know, to insert or remove an item at any index, besides the end of course, requires shifting all other items at a greater indexes to make room or fill the void. Its time complexity is the size of the list, so O of n. The structure of the list means each item has a fixed position, its index. But now, contrast that with the linked list, where the position of each item is not fixed. Each item knows its next item in the list by a pointer. So item positions don't really need to change, only change the pointers. You can insert and remove items anywhere in the list without moving the entire list. Just swap the pointers for that spot. It's constant time. For this reason, linked lists actually have a performance advantage over normal lists when implementing a queue or FIFO, where elements are inserted or removed at the beginning of the list. But they perform similarly to lists when implementing a stack data structure, so last in, first out, where elements are inserted or removed at the end of the list. So let's build that sweet O1 add to head method. Inside our racetrack class, which is a linked list, we're gonna create another method, and let's just call it add to head. If the self head is empty, just assign the given car to be the head, as that's the only car on the racetrack then. Else, in case there is already a car on the racetrack, we're gonna set the car's next pointer to point to the head and then set the head to become that car. So you can kind of see how we're now adding nodes to the left. Now, in the current version of your software, to add a car to the tail of the linked list, like you literally have to walk every single car from the head of the queue all the way to the last car of the queue. That's very inefficient. We need our add to tail method be all one time as well. And we can actually fix it by actually keeping track of the last item with the new data member called self tail. Now, since a single car on the racetrack could represent both tail and head, we need to assign both tail and head to that car. Else, set the tail's next pointer to point to that last car. And finally, at the end, that very last car that we're adding to the tail becomes our tail. And to make sure it works correctly, let's test it. So here again, our contestants from SR2 Demon all the way to R8. In this test case, I'm going to create two racetracks. The first racetrack will add every single car to the tail, and on the racetrack 2, I'm going to add every single car to the head. In the final output, as you can see, everything works as intended. So there you go. This is your fully functional O1 queue, done and dusted. Very cool. Alright, the drag racing management software sounds lit, but let's actually build something that actually uses the linked list data structure in the real world right now. LeetCode? I'm pretty sure that's the hardest Spotify. Like imagine if they'll ask you to reverse a linked list and you'll just lag or fail. You gotta get blacklisted, including your Wi-Fi provider. So don't be that guy who doesn't know how to reverse a linked list. Now comes the cool part, because I'm gonna show you visually how it works. But first, let's get you familiar with the source code of our music player. let's pick a music player as an example. Song will be our node that will store the title, duration of user song, and its reference to the next song in a playlist. And a music player is what keeps track of both head and tail in the playlist. Most of it really shouldn't sound that foreign to you by now. So let's apply theory to practice. Our test case is going to look something like this. A list of great songs, or more specifically their titles here, all added to our playlist from left to right as you can see them right now on the screen. Up there will be our function that stores the algorithm necessary to perform the transformation, in this case the reversal of our songs. And then in the end, we'll print the final result for double confirmation. So now, I want you to imagine those 4 songs laid out from left to right. This is a function with the parameter first song, which is a reference to the head of our playlist. It's what does the whole magic. So let's break it down line by line. As you know by now, in a linked list, items aren't sorted next to each in memory. So once you change the pointer, you lose the reference to the original node forever. So it's a good practice to use temporary variables. First, we'll create previous and current variables and set them to none and first song respectively. Next, we're going to throw current into the while loop. Since Gooba is our current song, we save its next pointer, aka Drake Scott's plan, into a temporary variable called next song. You'll see why in a second. I also color coded the variables so that you can see them a little bit better. Cool. Since our goal is to reverse these songs, let's set the Gooba's next pointer to now pointing to the previous, which we've just set to none. Next, on line 6, we'll set the previous variable to our current, and we'll advance current by setting it to our next variable that we've saved. Now, I want you to really think again why we even created that next song variable in the first place. Well, you can clearly see that Gooba's next pointer is now pointing to none, but as you recall, an item inside a linked list only knows its next item by a pointer, which we've essentially broken. The way to combat that? Just save it into a temporary variable. Exactly what we did with the next song. Because of that, we can now able to enter the second iteration of the loop. Our current song is now Drake Scott's plan, and its next pointer is pointing to Kanye's song, Power. Then on line 5, reverse the Drake's pointer to point to previous, which was set to Gooba in the previous iteration of the loop. Advance previous to now become the current, so Drake. Advance the current to now become the next song, so Power. I hope you start to catch the pattern here. I'll let it play so you can internalize. As our current is now none, the while loop terminates. But observe this function's return statement. It returns previous. Can you tell why? I mean, really think about it. If at the end of each loop we assign current to the value of its next pointer, eventually they'll both be none as we approach the end of the list, leaving previous as the tail. And since we reversed all the pointers, the roles are now flipped, and you can call noticed and new head now. Awesome. In case of having too much 6ix9ine in our playlist, we would need another feature in our music player for removing songs. Another good tip I can share is about using proxy nodes. Whenever you want to preserve the original order of nodes in a linked list, or songs in our case, it's a good practice to create a proxy node to guard against edge cases when returning the head. It also helps to keep the code more readable. So the first thing we're going to do is create a proxy node or temporary node with its next attribute pointing to God's plan, also the first song in our playlist. And since it's pointing to our first song, you can think of it as a new head of our playlist. Notice how we also save it into a current variable. Let's start advancing to the right. Our current is now the temporary node, and already you can see on line 5 that we're able to conveniently check whether the song its next pointer is pointing to, God's plan, is our target node. Well, it's not, so we go straight to the else statement, advancing the current pointer. Here we enter the second iteration of the loop, and since Drake's next pointer is our target song, watch what we're gonna do. Yes, simply jump over the song you want to remove. Essentially what we've just done is broken the pointer to Gooba. In case of C, of course, we would need to free that node to prevent memory leaks, but in case of Python, as I said before, it's being garbage collected. Now, what happens when you got them more than one in a row like that? Well, let's repeat the algorithm. Our current is Mr. Lemosi now, and we'll set its next pointer to point to that 6th cuba. So, .next. After which, we enter another iteration of the loop. But notice that our current isn't itself being advanced, only its next pointer. That's the key part in the algorithm. And now you can see why we're using double conditional. Our current is still on Lil Mosey's Notice song, but its next pointer is none, which means that we've reached the end of the playlist, and there's no more Takesha 69. Pay attention to the return statement though. Can you tell what's about to happen? Yeah, since we saved the reference to the original head of the list and not temporary variable's next pointer, we return exactly that. Do you now see why proxy nodes are useful? This one is straight from LeetCode, useless as a feature I guess, but really great at sharpening your funcs at the linked list data structure. So of course there are more than one way to figure out whether a linked list is a palindrome or not. One that I can think of, for instance, is just walking every node, saving each song's title inside of the array, and then simply drive index keys from both ends until they meet. Problem with that though is we have to create an additional array, so I guess we'll pass on that. Recursion is another alternative option. Here, we recursively advance the pointer while growing the call stack. And once we meet our base case of, reaching the end of the playlist, we return back to that last song. This is where we start to count back as we keep popping calls from the call stack, simultaneously comparing each popped song from the stack to the first song while also advancing the first song like you see here on line 10. But again, we still bump into the same wall of additional memory complexity, as each call adds a new frame to our call stack, consuming stock memory. What if we could just manipulate some pointers and, figure it out? There's a cool technique that we'll be using heavily throughout these problems. It's called two pointers. The slow pointer moves one song and fast pointer moves .next, just like you saw in that remove song problem we did before. Notice that this slow pointer always traverses the half the distance of the fast pointer, and vice versa. Knowing that, watch what we can do. Here's the code. Let's focus on this section first. So on line 2, I'll create slow and fast pointers both set to the first song, which is Gooba in this case. Next, we'll keep advancing both pointers until the fast pointer and the song in front of it reaches the end of the playlist. So while fast pointer and fast pointer .next. Here the slow pointer is advanced by one song, and fast pointer, just like we saw before, is twice that, so 2. And as our fast pointer reaches none, notice how this slow pointer lands in the middle of the linked list plus one node to the left. And really think why this might be useful to us. I mean, you can probably read now, so yeah, what line 7 essentially does here is calling our helper function reverse part, passing our slow pointer in it. Hopefully you do have a gist of the linked list reverse algorithm by now, so I'll let it play. Again, here we return the previous, or Gooba, which is now the new head of the list. Cool, so let's save it into a variable called last, and first here is just a reference to our original playlist. And I mean, you could sort of already tell why we even reversed the right half of the list, because all we're gonna do now to prove that the given playlist is a palindrome is to just walk every node while comparing each from both lists. And if every node from the last playlist matches the first, we'll just exit and return true right there. As we know, it's a palindrome. Here you have two playlists, songs A and songs B. Notice both of these playlists are sorted by duration from the shortest song to the longest song. Now you have to figure out how to build a feature for a music player that takes these two playlists and merges them into a single one in ascending order. So sorted. I'll give you 3 seconds to come up with the algorithm. Alright, we out of time. If you haven't come up with anything, don't worry, you just haven't subscribed to the channel to be able to figure out that the algorithm we need to use is actually the same one that's being used in the last step of the merge sort. Here, we simply follow the algorithm, starting with the proxy node, which, if you translate back to the original merge sort algorithm, could be thought of as a new array that will store our sorted songs. Next, create 2 pointers, each pointing to the beginning of its respective playlists. I color-coded these in red and lime. And following the algorithm, we need to compare the songs pointed to by 2 pointers, pick the shortest of 2, so Gucci Gang in this case, and append it to our temporary node. Now, of course, we cannot just append because that's a linked list, so what we can do instead is to grow a new pointer from the temporary node to that shortest song. And now we have to move the pointer of the playlist from which the song was taken to the next song. So move it to rep star. And since our temporary node also follows the linked list data structure, it needs to be advanced too. I created that wide bounding box, or square really, so you can keep track of it. From here, repeat the comparison and selection process until one of the pointers reaches the end of its playlist. Playlist A becomes none, so we're about to terminate from the while loop. Now, we can just hand back our playlist like that, since this would leave out great songs like, Rockstar, Love Sosa, Sycamore, and Bad and Bougie. The good news is that these songs are already sorted. And also, notice where our temporary node is currently at. It's on Peaches. So the final step here is nothing more than just making the Peaches next pointer, instead of pointing to none, point to Rockstar. In code, it translates as follows. Check which of 2 pointers hasn't reached the end and link the last shortest song we found to it. So basically, we're going to link temporary node, which is our Peaches, to the playlist B, which, in this case is the Rockstar. At this stage, if you draw the line through the entire playlist following the direction of each pointer, like that, you'll get a single perfectly sorted playlist as a result. How cool is that? Cool, merging 2 playlists doesn't really seem that complicated. What about 3 though, or more? Well, in that case, you would need another skill to be able to merge multiple playlists. There's a cool problem in LeetCode called K-sort that we absolutely must have as a new feature for our music player. You can assume you have 3 playlists, each has a varying number of songs in it. And just like in the previous example, you can also assume that these are all sorted. So from the shortest song to the longest song. However, note that these playlists are given to us in the form of a single array, or list in Python. And since we're working with a linked list, of course, each starts from its head. It looks something like this. Now you do already know how to merge 2 playlists, but here we have 3. So how about we take the first 2 playlists, sort them first into a single one, just like we did before, and then repeat it with the next 2 playlists. You can then kind of tell where that K comes from. But remember, our objective here is still a single fully sorted playlist as the final output. So let's focus on merging the red and blue part. First, let's create a list called updated playlists. This is where we're going to store our merged playlists. And since we're merging 2 playlists at a time, inside of our while loop, I indicate that by setting our step to 2. Here on line 4, part A represents the first index of the step, and part B the second. But pay attention to line 5. I added the if conditional to avoid the edge case of, going out of index in the playlist array. Now, I'll abstract away the merging process as we already covered it in great detail in the previous example. So this will be a single sorted playlist, the head of which we're gonna append to our updated playlist array. But remember, we're going 2 steps. So here's our second iteration of the loop. I is now 2. And since this playlist doesn't have a pair, part A will store the entire playlist. So Peaches and bank account. And part B is just none. There's nothing to sort, so merge sort function just returns part A in its current form, and we just append that as well. You can clearly see that the updated playlist array now stores both heads of our merged playlists. That is purple and lime. The objective hasn't been met yet, so keep iterating. Here, we repeat the algorithm. Awesome. Now, we have a single, complete playlist. So let's again append its head to the updated playlist array. On line 8, overwrite the original playlist with our updated playlist, and exit out of the while loop. Here, we just return the head of the merged playlist itself, linked to all these songs. This algorithm is quite efficient, since instead of continuously merging each playlist, we're essentially splitting up the work by going 2 steps at a time. But of course, because we don't know how many songs will be in it, the iteration is still required, and this operation, as you might know, has a linear time complexity. So given k playlists with total number of songs n, the big O of this algorithm would be actually log n k, or just log n if you want to drop all the constants. Let's take a look at this playlist. As you can see, it's unsorted. Can you partition it such that all songs shorter than, say, Peaches, so anything less than 3 minutes and 18 seconds, come before songs longer than Peaches? You should also preserve the original relative order of these songs in each of the 2 partitions. Knowing proxy node technique, here's how I would solve this. I create 2 proxy nodes. Short songs node will store all songs that are shorter than 3 minutes and 18 seconds, and long songs will therefore anything longer than that. And the algorithm here is really as straightforward as it can be. If the song is shorter than Peaches, I just set the short song's next pointer to that song, and then I simply advance the pointer to the next song. And this is where we reach the end of the playlist. Now, I just need to connect short songs with long songs. And since I've been advancing each node, I know that both of them sit at the end now. So, Ransom for the short songs and Bad and Bougie for the long songs, respectively. For this reason, in the beginning here, I created these 2 additional variables to save the reference for each proxy node. So let's link them up. I'm going to set short song's next pointer to proxy R, or proxy right, dot next. But what a bummer, I created an infinite loop here with the pointers. The solution is obvious here, but still take a moment to brainstorm for a sec. Because I got a reference to Bad and Bougie, well, this is as simple as changing its next pointer. And that's the partitioned list. Now, if you use Python on the daily, if you're cool, you may have heard of this Python method for swapping elements in the array. And I mean, this is true magic. So let's say this is our playlist of some great songs, and I want to swap every 2 songs in it. I can literally do this in 3 lines of code, discounting the print statement. So watch. I'm going to create a for loop that's going to loop through this entire list with the step 2, and I'm going to index into the first song, then I'm going to index into the song to the right of it, and I'm going to do this. If you observe the final output, we've just swapped every second song in the playlist. How cool is that? Now you can make a linked list, do the same thing. Just a bit more, pointer manipulation stuff. Let me show you. To swap 2 notes or songs, we must obviously have a pair. So first song and its pointer should exist. Let's handle that exception in case we don't. Proxy node, as always, to avoid edge cases. Let's start the algorithm. Our current song is Blueberry Faygo. I'm also going to need to save the third song, which is equivalent to saying .next. as well as the second song from the playlist. Here, I'm trying to swap Blueberry Faygo with New York State of Mind, so reverse next state of mind's next pointer to it. I then set Blueberry's Faygo's next pointer to Roxanne. Hope you now see why we even need that variable called third. On line 7, I set previous to now pointing to New York State of Mind, or our second variable. That's the swap. Lastly, to prepare the algorithm for further iterations, I'm going to shift both previous and current to the left. And at this point, I'll let the code do its job. Now pretend there's a bug in our music player. Someone was working on our software and say introduced a infinite loop. That just messed up the pointers. You're gonna fix it. But of course, before fixing it, you first have to figure out where the loop even begins. Because, that's not an array, that's a linked list. First idea that comes to mind, whenever encountering something like a infinite loop, is just to use an additional array, or even something like a set in Python, where we iterate through every single song in the playlist, comparing it against, already visited songs. The time complexity of this algorithm would be just O of n, unfortunately just as its space complexity, because of that additional memory array we have to create. But how about doing it in constant memory space? As you might have guessed, we do gonna need Floyd cycle detection in the algorithm. Now, arbitrarily, the hardest part about this algorithm isn't actually code, but rather math behind it. So let's break down visually why it works. Let's define parts of our playlist. So the right part is x. It represents the distance before the cycle begins, or the infinite loop in our case. And our y is gonna be the first part of the cycle up until the meeting point. I color coded it in lime. And part Z, the pink part, is the length starting from the meeting point. L just means the length of the cycle itself, so Y distance plus Z distance. And M is the distance to the meeting point. Now, do you remember that slow fast pointer technique I covered earlier in the video? Well, if the tortoise travels distance is x plus y, then the hare will logically traverse the list twice as fast, or 2 times x plus y. And here's what we're trying to prove. We want to prove that the remainder of when distance x is divided by the cycle length L is precisely the number of steps from the meeting point back to the start of the cycle. In other words, if we mod x by the length of our cycle, the remainder will be equal to the z part, that pink part. So we know that our hare distance is 2 times x plus y. Well, we can also represent that as m times certain iterations of cycle L, or just CL. C in this case can range, from 0 to infinity pretty much. Well, you know that m is just x plus y, so let's unwrap that. Canceling out x plus y from this side, now leaving us with x plus y equals CL. And I'm gonna isolate x to the left, so I'm gonna move y to the right. Now let's mod both of them by the length of our cycle. Again, we don't know how many cycles it's going to loop, so we can imagine CL as, some amount of L's. What we do know though is that one cycle goes into one cycle exactly one time, so, L mod L will just cancel out completely. Now, if we mod L minus y by L, of course we'll be left with the negative y. So let's adjust that by finding the positive equivalent. So simply add L to the negative part. But look, L is just y plus z. So effectively, if I cancel out both y's, this would mean that x mod L does equal z. To prove that it actually works, let's run the algorithm. Here the tortoise moves .next and hare moves .next. And you already know what it means. The start point is our meeting point, I guess, so let's break. Here at line 12, we set the tortoise back to the start of our playlist, And now we're gonna drive both hare and tortoise by one step. Watch what happens. I'll stop right there. So just doing math real quick, I know that X is 4 songs long, just like Z. I also know that my cycle is what, like 1, 2, 3, so 7. Well, 4 modulo 7 is 4. So our math adds up. And that's our beginning of the cycle. Earthquake. Now, up until this point, you've been working with this singly linked list, but we can actually go backwards if we add previous attribute to our music player class. And to manage our user songs more conveniently, let's actually build some, abstract methods that will allow for an easy add song and remove song operations while using memory as efficiently as possible. Sounds like impossible, but we can actually achieve this by designing what's called a circular queue. Now, I want to clarify right away that the double linked list isn't probably going to be the great example to showcase the idea behind the circular queue. Uses even more memory because of that extra previous pointer address that we have to store in every single node. So I'm only doing this to strengthen your understanding of pointer manipulation. So we'll first design the circular queue using an array, as we should, and then we're going to do the same, but implementing it as a double linked list. So the idea behind the circular queue is pretty simple, more efficient memory allocation. And if you remember, C, for example, always requires you to define the size of the array. And, since you can modify it later after it's been declared, the circular queue is so cool and great because, well, you can reuse that space once the buffer becomes full. So even though we're using Python here, we can still imitate the process. Let's build the circular queue class. First, I need the queue itself, and I will build this using a list comprehension where K is the size of the queue. And so space is, but we'll keep track of how much space we're using so that we don't go over that buffer. Now, the key components of a circular queue are the front and rear pointers. Both are keeping track of the first song in the queue and the last song inside the queue. Both initially set to -1 to represent that I currently have no songs. Notice when I add the first song to my queue, both of my front and rear pointers will be set to 0. Well, as they should. And if I keep on enqueuing random songs, notice how I'm adding them to the rear in the clockwise direction, incrementing the rear pointer's index by 1. But same for the dequeue method. I'm shifting the front pointer in the same clockwise direction. And when I say shifting, I mean it. Like, I don't remove them. All songs you're seeing right now that are slightly faded out do still stay in memory. It's just for us they don't exist anymore. Now, I can just keep incrementing the index of the rear like that because, well, think about it, right? The index 8 or above just doesn't exist in an array of 8 elements. So the way we get around that is by using a modulo, since 8 modulo 8 would put us back to the 0th index. So here I'm about to add Drake. Our self rear is at the 0th index, clearly. And queuing it one more time turns it into 8. So it goes straight to the 0th index, effectively taking the place of the last song, Blueberry Faygo. But the coolest part is that it continues to work because, well, every index will always be less than the length of the array. Now, we also don't want our rear pointer to surpass our front pointer, since, this would start overriding our songs that we don't want to be overwritten. We do this with the isFull function. Here, it blocks the rear pointer from going any further because our queue is full. Cool. Now, same circular queue, but build it with the double linked list. Here, instead of indices, we're going to have nodes. And, the word doubly means that we can go forward and backwards. So I'm going to extend our song class with a new data member called self_previous. The self_first here will just take the role of the front of the queue and self_last the rear. To make it circular, I connect the self_previous pointer to the first, and I connect self_first next pointer to the last. First thing we're going to do, after checking the queue isn't full of course, is create a song that we're trying to add. Let's pick Blueberry Faygo. See that red arrow pointing to first? It's the last's previous pointer. And to avoid losing reference to it, I'll save it into a variable called passPrevious. On line 7 here, I'm going to grow the previous pointer from our new song back to that passPrevious. Since Blueberry Faygo is now coming right after our first song, change the passPrevious next pointer to point to it. Link Blueberry Faygo's next pointer to the last node, and finally set the last node's previous pointer to Blueberry Faygo. Notice how we conveniently squeeze that song in our music player. And because we restrict the amount of memory being used, the allowed space in our queue should diminish. Let's add another song, perhaps Distraction by Paul G. Capelot. And same algorithm. Nice. Now let's try the DQ operation. By this point, you do know how FIFO works, right? Blueberry Faygo was the first song that was added, so it goes out first. You also remember how to remove songs in the playlist. Yes, just breaking pointers to the target song. Kind of like jumping over. Looks like we've freed up some space, so let's increment. In here, at this point, I want you to take a minute to really internalize the process. So for the final animation here, I thought, why not just do some intense pointer stuff? How about we add yet another useful feature to our music player app? The ability to sort songs by their play duration. I think that's pretty unique. But for a sorting algorithm, we're going to go with something number one, fun, number two, inefficient, the insertion sort. Now, to make our life a little bit simpler, we could actually use something like a double linked list. So of course, we're not going to do that. For this case, here are the songs you're working with, and also notice that none of these are sorted. So let's lay them out from left to right. As you can see, our proxy node is set to -infinity, but its duration isn't really that relevant, so honestly you can just set it to whatever you want. For the attributes, previous is being set to whatever the first song in the playlist is, and current is whatever Blueberry Faygo is pointing to. So in our case, it'll be New York State of Mind. So let's start the while loop. On line 2, we basically check if the current song is longer or the same length as the previous song. If that's true, just advance both pointers to the right, since, that's what ascending order does look like. Now, in case it's not true, like here, you see that Roxanne is clearly shorter than New York State of Mind, you have to edit to the back, but not just somewhere to the back. We need to account for the duration of every song that's to the left as well. On line 5, you see that I'll create a temporary variable referencing that gray proxy node and compare my current song, Roxanne, against the song my proxy node is always pointing to. In this iteration, if you follow its pointer, you'll see Blueberry Faygo. Since Roxanne is shorter, I'll exit right away. Then go to line 9 to shift the previous pointer to the next song of the current, change the current's pointer to Blueberry, and then change the temporary's next pointer to Roxanne. Pay attention to line 12 now. Notice how conveniently we're advancing the current, all thanks to that line 9 where we shifted the pointer to Earthquake. So now, if you even out the pointers, it's like you're inserting Roxanne into the right spot. Okay, here we enter the second iteration of the loop. Our previous is still New York State of Mind, and of course Earthquake is shorter, so we go straight to that else statement. Go back to our temporary node, and start checking from the start again. Earthquake is longer than Roxanne, so we increment the pointer. Same for Blueberry. And New York State of Mind is of course longer, so we exit out. I don't want New York State of Mind to point to Earthquake anymore, since we're going to be editing it to the back, so set it to whatever Earthquake is pointing to. Set our current to temporary.next, set temporary to now pointing to Earthquake, and advance the pointer. Now, the type complexity of this algorithm is O of n in the best case scenario. That is, every song is already sorted since it doesn't require any pointer manipulation. But in case they're not, like in our example, this would be big O of n squared because of that nested while loop. There are, of course, many other more efficient sorting algorithms out there, but it was really my goal with this video, showing you the most efficient way. It was really about giving you the mental model for what the linked list is and how its pointers being manipulated together, because there's just something cool about that. Hope you enjoyed it.